The substituents on a benzene ring can influence the electronics of the pi system to make it a better nucleophile or a better electrophile, and stabilize the various intermediates that we encountered in the reaction pathways shown in the previous webcast. There are two ways that these substituents can interact with the pi system. One is by what's known as inductive effects, and that's what we'll look at on this slide, and the other is through the kinds of resonance interactions that involve the pi system entirely. Substituents can withdraw electron density from the pi system to make it a better electrophile, or substituents can donate electron density to the pi system and make it a better nucleophile. Substituents that act by inductive effects, such as this trifluoromethyl group or this methyl group on the benzene ring, involve sigma and sigma star interactions with the pi system. We can look at the frontier molecular orbitals in order to decide how these substituents influence the electrons in the pi system. An electron withdrawing group is going to have its greatest effect on the LUMO and make the pi system more electrophilic. You can see from the LUMO of this trifluoromethyl group that it's the sigma star orbital that's interacting in a pi to sigma star pi type interaction that depletes the electron density from the benzene ring, making it a better electrophile. Electron-donating substituents, such as this methyl group on benzene, have their greatest influence on the highest occupied molecular orbital. In the case of this methyl substituent, it's electrons that are occupying the sigma bond of this carbon-hydrogen bond that donate in a sigma to pi star, pi-type interaction and increase the electron density in the pi system of the benzene ring to make it a better nucleophile. When we talk about better nucleophile or better electrophile, in all cases we're comparing it to the reference case in which there is no substituent on the benzene ring, just a hydrogen atom. Now let's take a look at some substituents that interact with the pi system through resonance. First, we'll look at electron-donating substituents, and these usually involve non-bonding pairs of electrons on substituents that are bound to the benzene ring. A typical example would be the electron lone pair on the nitrogen of this aniline. We can see that it donates its pair of electrons into the ring by an N to pi star pi-type interaction, and creates the resonance contributors that are seen here. Notice that the electron density from these resonance contributors is on every other atom. And when we look at the highest occupied molecular orbital, we see that there's an interaction between the substituent and the pi system, and we notice that there's a large coefficient of electron density on those two atoms as well as on this atom. But notice the smaller amounts of electron density that are on these two atoms. And so you should see a consistent picture between the highest occupied molecular orbital and the places where the electron density is greatest and these resonance contributors. Electron-donating substituents have their greatest influence on the HOMO and have very little interaction with the LUMO, but that's just the opposite what we see with electron-withdrawing substituents. In the case of electron-withdrawing substituents, there'll be a resonance-type interaction if there's a low-lying pi star orbital on that substituent, such as we might have with this polarized pi bond. When we look at the curved arrows associated with this resonance interaction, we see electron withdrawing from the benzene ring pi system into the pi star of the carbonyl group. That creates a positive charge on the benzene ring in the three positions that are shown here. We can see from the lowest unoccupied molecular orbital why this substituent creates a better electrophile in the pi system. First, notice there's a strong interaction in the LUMO between the substituent and the pi system. Second, notice that where we see the greatest concentration of the lowest unoccupied molecular orbital coincides with the position of the positive charge in these resonance contributors. Notice also that there's very little interaction between the HOMO and the substituent. And so, electron-withdrawing groups have their greatest influence on the LUMO, making the ring more electron-deficient and a better electrophile. In this webcast, we've seen how a substituent on a benzene ring can influence the pi system's electron density, and these changes take place at certain sites on the benzene ring. In the next webcast, we'll see how these substituent effects can favor and activate certain pathways for substitution while disfavoring other pathways.